Okay, so next we will show that multiplication is distributive over addition in the rationals. So proof. Once again, let q sub I be a rational number. Then q sub I is of the form m sub I over n sub I, where m sub I and n sub I are integers, and the integer n sub I is not 0. And so the sum, q sub 2 plus q sub 3, is a rational number as the rational numbers, is closed, the set is closed, under addition. Similarly, the product, q sub 1 times the sum, q sub 2 plus q sub 3, is a rational number, as the set of rational numbers is closed under multiplication. Further, the product of q sub 1 with the sum, q sub 2 plus q sub 3, is the product of the ratio m1 to n1 times the sum, m2 to n2 plus m sub 3 to n sub 3. Now, as multiplication is a distributive over addition for the integers, then we can distribute over the numerators and the denominators, and so we have m sub 1 times m sub 2 over n sub 1 times n sub 2 plus m sub 1 times m sub 3 over n sub 1 times n sub 3. Now, as multiplication is commutative over the integers, we can rewrite this as m sub 2 times m sub 1 over n sub 2 times n sub 1 plus m sub 3 times m sub 1 over n sub 3 times n sub 1. And this is the sum, m sub 2 over n sub 2 plus m sub 3 over n sub 3 times m sub 1 over n sub 1, that is the sum q sub 2 plus q sub 3 times q sub 1. And so multiplication is both left distributive and right distributive. Over addition in the rationals. So it is simply distributive over addition. So evidently, the rational numbers, together with normal addition and normal multiplication, is a ring. However, the set of rational numbers admits a richer structure than a ring. Now we will move towards defining that structure. So first, we prove a theorem. Let A and B be rational numbers. Then, the product of A and B is 0 if and only if Either A is 0 or B is 0. So proof. Let the product A times B equal 0, and suppose that A is non-zero. Then the rational number B is a solution of the equation A times x equals 0. Now for every non-zero rational number, that rational number has the form, the ratio of m to n, where m and n are both non-zero integers. And so the inverse, which is n over m, is also a non-zero rational number. And so we can multiply the non-zero rational number a by its multiplicative inverse, which is 1 over a, on both sides. Now, as multiplication is associative for the rationals, we have 1 over a times x equals 0, since the product of any rational number with 0 is 0. And so we simply have 1 times x equals 0, or x equals 0. This is the entire solution set. And so the rational number b must be 0. Similarly, a times b, if the product of a times b is 0, and b is not 0, then a is equal to 0. So the product of a and b is 0 if and only, well, if either a is equal to 0 or b is equal to 0. So conversely, suppose that a equals 0 or b equals 0, then the product of a and b is 0 in either case. And so now we can state that the product of a and b is 0 if and only if either a is 0 or b is 0. So as a corollary, we'll show that the rational numbers under multiplication has no zero divisors. Proof. Let a and b be rational numbers. Then, by the previous theorem, a times b is 0 if and only if either a is 0 or b is 0. So by the contrapositive, we have that a times b is not 0 if and only if a is not 0 and b is not 0. And one of the implications in this biconditional is that if a is not equal to 0 and b is not equal to 0, then the product, a times b, is not equal to 0. And so the rational numbers under multiplication has no zero divisors. Okay, so next we will show that the non-zero rationals under multiplication is an abelian group. So proof. Let q sub 1 and q sub 2 be non-zero rational numbers. Then, as the non-zero rational numbers is a subset of the entire set of rational numbers, the numbers q sub 1 and q sub 2 are rational numbers. And so the product, q sub 1 times q sub 2, is a rational number. Now, as the rational numbers under multiplication has no zero divisors, the product, q sub 1 times q sub 2, is not equal to 0. And so the product of q sub 1 and q sub 2 is a rational number that is not equal to 0. That is, the product, q sub 1 times q sub 2, is a non-zero rational number. And so we do have closure, and hence the structure consisting of the non-zero rational numbers under multiplication is a magma. So let q sub 1, q sub 2, and q sub 3 be non-zero rational numbers. Then, as the non-zero rational numbers is a subset of the entire set of rational numbers, the numbers q sub 1, q sub 2, and q sub 3 are rational numbers. And so the product, q sub 1 times the quantity, q sub 2 times q sub 3, is the same as the quantity q sub 1 times q sub 2 times q sub 3. That is, multiplication is associative over the entire set of rationals, and certainly also for the non-zero rationals. And hence the structure consisting of the non-zero rationals under multiplication is a semigroup. So notice that the number 1 is a non-zero rational number. Let q be a non-zero rational number. Then, as the set of non-zero rational numbers is a subset of the entire set of rational numbers, this number q is rational. And so 1 times q is equal to q times 1, which is q. And hence the structure consisting of the non-zero rational numbers under multiplication is a monoid. Now notice that up to this point, all the properties of the structure have relied on the properties of the entire set of rationals under multiplication. We now have a diversion from that. Let q be a non-zero rational number. Then q is of the form m over n, where both m and n are non-zero integers. And so the multiplicative inverse of q, which is n over m, is also a non-zero rational. And so q times q inverse is m over n times n over m, which is m times n over n times m, which is the same as m times n over m times n, which is 1. And q inverse times q is n over m times m over n, which is n times m over m times n, which is the same as n times m over n times m, which is 1. And so we have that q times q inverse is the same as q inverse times q, which is 1. And so every non-zero rational number has a multiplicative inverse, and hence the structure consisting of the non-zero rational numbers under multiplication is a group. Now let q sub 1 and q sub 2 be non-zero rational numbers. Then, as the non-zero rational numbers is a subset of the entire set of rationals, q sub 1 and q sub 2 are rational numbers. And so the product q sub 1 times q sub 2 is the same as q sub 2 times q sub 1. And hence multiplication is commutative over the non-zero rational numbers as well. And so we have that the non-zero rational numbers under multiplication is an abelian group. So now we need a new definition. A field, which is denoted as a set F together with some notion of addition and some notion of multiplication, consists of a single underlying set which we'll call F, together with two binary operations, some notion of addition and some notion of multiplication, such that first, the entire set under addition is an abelian group. Second, the non-zero elements in the set under multiplication is an abelian group. And third, the distributive law holds that is, for every three elements, A, B, and C, in the set F, the product of an element A with the sum B plus C is the sum of products AB plus AC. Now notice that as multiplication is associative, as multiplication is commutative, both the left and right distributive laws hold, and so we simply say the distributive law holds. So evidently, the rationals, together with normal addition and normal multiplication, is a field, while the integers, together with normal addition and normal multiplication, is only a ring. So notice that every field is a ring, but not every ring is a field.